Hello all, welcome back. I'm Ruthvik, and in this session, I'm gonna take the PCD for Codeforces round Hello 2026. And in this session, I'm gonna discuss the first five problems of this contest. Okay, let's start. Coming to the first question, Alice and Bob are playing a game on an array of size n containing only numbers 0 and 1. Okay. Alice moves first, with each player alternating the turns. In a player turn, she chooses two integers L and R, and we have to note the condition that L is strictly less than R. So at least a player has to choose two elements. Then the subarray L2R is replaced with a single number 1 minus minimum of all the elements from L2R. That is, if all the numbers in subarray are 1, then the minimum is always obviously 1. So it is replaced by number 0. And otherwise, if the subarray contains at least one 0, then the minimum in the subarray will be that 0 and it will be replaced by 1. Okay? And the game ends when there is exactly one number left in the array. Alice wins the game if the final number is 0. Otherwise, Bob wins the game. Okay. We have to determine who wins the game if both of them play optimally. For example, I'll go through the first test case. Here, in the first test case, what Alice will do is Alice will initially choose L equal to 2 and R equal to 3. What will happen here is L2 R3 means this is the subarray chosen by Alice, and here the minimum element is 0. So these two numbers will be removed and 1 minus 0 is 1. So it will be replaced with a single integer 1. Okay. And the array becomes 1 comma 1. At this point, Bob has only one option. He he has to choose at least two elements in the subarray, right? So he will choose the subarray one entire array. He has no other option, and he will replace it with 1 minus minimum of a1 a2, which is 1, and the final element will be 0. So the game ends and Alice wins the game because the last number is 0. Okay, let's go to the explanation. Here, first let us see what is the winning condition for Alice. Like in what case Alice can win in a single move. If all the elements of the array are 1, Alice can simply select the entire array as subarray and replace it with 1 minus 1 that's equal to 0. Replace it with a single element that is 0 if all the elements are 1. And a winning state for Bob is if there is at least one 0 in the array, no matter where the 0 is, Bob will simply choose the entire array, and 1 minus minimum of that entire array will be 0, right? So the final element will be 1. So Bob will win the game if there is at least one 0 in array in his turn. Okay. So what Alice has to do is that uh, either if array contain if array contains all ones, Alice will directly win the game, or Alice has to return an array to Bob in such a way that it contains only two ones. Because if there are only two ones in array, Bob has no other option but to conduct an operation on these two ones, and the final element will be 0. Okay. For that, the key observation is that if there are all ones, then our answer will be obviously Alice. All one case. Now, doing some little casework, we can see if there is at least a 1 on either of the ends of an array uh, and zeros in between. Like it's not needed that 1 should be on two sides of the array and at least one side there should be a 1. Then what Alice can do is Alice will select the remaining part of the array and she will conduct an operation on this remaining part. And what will happen is that as remaining part contains at least one zero, it will become a one. It will be replaced by a one, and Bob will be left with this array. And he will be forced to do the only operation on the entire subarray, and the final array will contain only zero. So it's a winding condition. So we can see that this is the only requirement. If there is at least one at either of the ends, then it is a winning condition. If there are zeros on both the sides of an array, then no matter what Alice does, no matter which subarray Alice chooses, after one operation, she will be uh, after applying one operation, the resulting array will contain at least one zero. So, as the resulting array contains at least one zero, Bob wins in this case. So, simply the code for this question is if a of 0 or a of n minus 1, either of the sides is equal to 1, then Alice wins the game. Else, Bob wins the game. Okay, now I'll show the code for this question. Here we are checking if either of the sides is 1, I'm printing Alice. And if and in other case, I'm printing Bob. And that's all. Okay, coming to the second question. The name of the question is yet another mixed problem. You are given an array A of length n and an integer k. Okay, let's define f of LR to be the value of mix of elements from elements in subarray L to R. Basically, it's a mix of elements from AL to AR. Okay, we have to like you want to perform this operation exactly n minus ka plus 1 times. So what we are doing is let the current length of sequence be A. You need to find a interval LR of length k such that max of all the mixes is equal to f of like basically I'll explain the question. So the operation we are permitted to do is that we have to select an interval LR such that uh, LR of size k such that the value of mix of the subarray containing LR is maximum possible among all the subarrays of size k. Maximum of I equal to 1 to a minus k minus 1. Basically, here he is taking the max of all the subarrays of size k, and that value should be equal to the mix of our chosen interval. And we can perform this operation n minus k plus 1 times. And finally, after n minus k plus 1 operations, we will be left with a sequence of length k minus 1. And our objective is to maximize the mix of remaining elements. And we have to output the maximum possible mix. Yeah, and input is we are given n and k and also n integers, the elements of the array. Okay. So I'll take an example. Here in a third test case, we have to perform following operations. Here, the maximum value of mix of all windows of size 3 is 3. So they have chosen I equal to 1 and j equal to 3. And they have removed A2. Like basically, A1, A2, A3 is our chosen subarray, and then we remove A2. And the sequence now is 0 to 1, 0. Next, we choose I equal to 2 and j equal to 4. Then we again remove A2 from the element from that subarray, and our sequence now is 0, 1, 0. And finally, we select I equal to 1, j equal to 3, and then remove the first element from this I equal to 1, j equal to 3 is basically the entire array, and we remove the first element, and the sequence now is 1, 0. Process terminates, and the final mix is 2. Okay. In this question, in the contest, I initially started by analyzing the upper bound of the answer. Like finally, we will be left with k minus 1 elements, right? So the maximum possible mix of k minus 1 elements is what? Uh, K minus 1. Yeah, we'll be left with k minus 1 elements. So the maximum possible mix of k minus 1 elements will be 0, 1, 2, so on to k minus 2. So our answer, maximum possible answer will be k minus 1 itself. Or, or if the array does not contain all the integers, like from 0 to k minus 2, then we can get the mix less than k minus 1. So our answer will be mix of the array. So the maximum upper bound of the answer is minimum of k minus 1, comma, mix of the array. Okay. From here, uh, it's surprisingly this upper bound will be our answer. The proof will be as follows. Like let this value be tar, or some, for simplicity, I'll take this value as x. Okay. Now, what are our operations? In one operation, we have to choose an array of size, subarray of size k, and remove one element from it, right? So, uh, let's suppose we are at some ith operation. So there are only two possible cases. Either the max mix is greater than or equal to x, or the max mix is less than x. Okay. In the case when max mix is greater than or equal to x, then what we will do here is simply my final goal is to make the mix of the remaining elements x, right? So if my max mix is greater than or equal to x, or I'll take greater than x, and the second case will be less than or equal to x. If my max mix is greater than x, what I'll simply do is greater than x means we have a term x in the array, like we have all the integers 1 to x. Then in this case, I'll simply remove the element x, or any element which is greater than or equal to x. Okay. So in that way, if the max mix is greater than x, I'll remove this element. Now coming to the second case where max mix is less than or equal to x, we have k elements, and the max mix of these k elements is less than or equal to x. So here, one of the two cases is possible. Either it's possible that 1, 2, and there is a missing number 4, 5, so on till and x minus 1 as follows. Yeah. Only this one is possible. Like 1 to x, we have a missing number here. To have a max value x, we know that we need only k minus 1 elements. Like k minus 1 elements are sufficient. Here, in this case, we are having k elements, and our value of mix is less than or equal to x. So this tells that there is definitely an element that is repeated. So in this case, if my max mix is less than or equal to x, I'll remove this repeated element. Okay. If it is greater than x, I'll remove the value greater than x. I'll remove the value which is greater than or equal to x. And if it is less than or equal to x, I'll remove the repeated element in that range, in that subarray. Okay. So in this way, I'll do the k minus 1 operations, and finally we'll be left with a subarray of size k minus 1, which has the max value equal to x. And that's all. I'll go to the code of the second question. So initially what I did is, as we know that our final answer is either mix of the final answer is either k minus 1 or mix of array. What I did is simply I removed all the duplicates from the initial array and I initialized the mix as 0. Basically, I'm finding the mix of the array, and here the count is k minus 1. If the mix of the array is less than k minus 1, then the for loop will break and I'll print that mix value. In the case where the mix of the array is greater than k minus 1, what will happen is the for loop will only run k minus 1 times, right? So when the mix value reaches k minus 1, the for loop will break and see, and that's all. The max value will be set and I'll output the value. Simply, this is basically similar to printing the value minimum k minus 1 comma mix of a, and I have implemented like this in the contest. Okay, now let's move on to third question. Coming to the third question, there are n bases in a line and kth of which being the home base of our army. Okay. Initially, there is a single soldier at base K, and each day following happens in the order. You give out an order choosing base I and any number of soldiers in that base. Okay. The number can be 0 or all the soldiers in that base. And we tell all the soldiers to move to either base I minus 1 or I plus 1. Basically to the left or right base of our current base. Okay. Current in the sense of our selected base. Now all soldiers must move in the same direction and no soldiers is allowed to move to the left of base 1 or right of base n. Okay. Then at every step a new soldier moves into base K, and this soldier cannot be ordered by the days commands. So we have only M days until enemy attacks, and we call a base fortified if there is at least one soldier in that base. Our job is to find the maximum number of fortified bases, given we have the time till the end of the mth day. Okay. In input, we are given three integers n, m, and k. And finally, we have to print the maximum number of bases we can fortify till the end of m day. Basically, maximum number of bases which contain at least one soldier by the end of m day. And also, I guess the sum of n across all test cases does not exceed 2e5. It's bounded by 2e5, so we can write a O of n solution. Uh, okay, now let's move on to the solution. Here, what we have in the question is that, like, suppose 1, 2, so on, I have a base k, which is my home base, and finally base n. Okay, and every day, one soldier keeps on getting added to my base k. So, what I can do is, suppose if there are 10 soldiers in my base K, I'm just taking an example. I can either move 10 soldiers in base K or some another base 1, 2, 3, 4. Some in base 5, I have some 15 soldiers. Okay. In one operation, I can either move these 15 or any number x less than or equal to 15. Like for example, I'll move some 8 soldiers to base 4 in one operation. Or I can also do this. I'll move some 8 soldiers to base 6 to right or left side of my current base. And also if I want, I can move all 15 soldiers to either of the bases 4 and 6. Okay. So here, the first observation we have to make is that we have to see like how much distance I can cover left and right from my current base. Okay, let the distances be x and y. So the most optimal way to cover distance x is that, let's suppose if there is a soldier at a distance x from my base, my home base. So I have no other option other than to spend X moves on that soldier. Like I have to first move him from K to distance 1, 2, 3, so on till X. So I have no other option other than to move him X times. So what's best is that if I want to have a soldier here, I'll initially wait till I get X soldiers in my home base, and then what I'll do is I'll move all X soldiers from here to 1. All X soldiers will come here, and here at the end of the day, I'll get one soldier. And next step will be I'll move X minus 1 soldiers. Here I'll move X soldiers. Here I'll move X minus 1 soldiers from here to here. What will be left here is we'll be left with one soldier. Uh, okay. Now I'll move X minus 2 soldiers to the next base. And again we'll be left with one soldier. In this way, if we continue this process, we'll be left with one soldier in every base, and at the final base X also we'll be left with the one soldier. X minus 2, X minus 3, X minus 4, so on. Okay? So basically, first what I'm trying to do at base K, initially I have one soldier. Okay? So let me count the number of days. So I have to wait. I need X minus one more soldiers. So I have to wait for X minus 1 days. Okay. Plus, now what will happen is, now we have X soldiers, right? So I'll move them to X steps towards left. Okay. That will take another X days. Okay. While moving these soldiers X steps, what will happen is, this base will be repopulated, all X soldiers will become 0. And as I have waited for X days for all the soldiers to move, this base will have X soldiers now. Okay. Now my second target is to move Y soldiers towards right. Uh, to be more precise, I want to cover Y forts towards the right. So I have to wait for Y minus X more days. Without loss of generality, I'll assume that Y is greater than or equal to X. I have to wait for Y minus X days. So here initial X minus 1 days and X days for waiting for all the soldiers to move and fortify the X bases towards left. And again Y minus X days, the Y minus X days waiting for the home base to be populated with Y soldiers. And again, similarly, I'll move all the Y soldiers in Y days plus Y days. Okay. So what's happening here? X minus 1 days are initially we wait X minus 1 days for population to become X. Then we move those X soldiers. We wait for population to become Y. And then we move those Y soldiers. Okay. So here, total number of days is, if we cancel X and X, what we'll get is X plus 2Y minus 1. Okay. Total number of days needed to cover X forts to left and Y forts to right. So in these many days, I can cover X plus Y plus 1 forts. Because we are covering x here, y here, and basically 1 is our home base. In these many days, I can cover x plus y plus 1 fourths. Okay. So now our next step is to see, uh, find some optimal values of x and y such that 2x plus 2y minus 1 is less than or equal to m. This can be done. We have to notice, I initially noticed a fact here that if I can cover x plus, I can cover some, suppose some t fourths, then I can obviously cover t minus 1 fourths, right? So, this monotonicity leads me to, this monotonicity allows me to apply binary search. So we can simply binary search on value t. The t is the number of votes. T is basically the final number of votes, and we can binary search on this final t to get the optimal x and y values. And how we are binary searching here is that, let's suppose, uh, if we have fixed a value t, then basically x plus y plus 1 equal to t in the binary search. Okay. From here, we can see that, uh, basic, I guess this will be better if I explain this question with the code. Here, the term x plus 2y plus 1 equal to m, or less than or equal to m minus 1, right? This term will be most, like x plus 2y minus 1 will be most minimal if the following y value is as low as possible, because initially our condition is y is greater than or equal to x, right? So y, I can simply write y as some x plus k, where k is some non-zero number, is less than or equal to m. So for getting the minimal possible value, what I can take is I'll take k as 0. Okay. Okay. I was not sharing the screen. Hmm. Yeah, or I'll try explaining from the code itself. Here we have base k. So at most, we have, x value can be less than or equal to k minus 1 only, because at most we have k minus 1 bases. We have exactly k minus 1 bases to the left of k, and y value must be less than or equal to n minus k. Because we have exactly n minus k bases to the right of k. Okay. And here, without loss of generality, considering that CL is less than CR. Like if CL is greater, I'll simply swap it because X and Y are interchangeable. So initially, I'll try to make the value X as large as possible because as I have discussed earlier, in the term X plus 2y minus 1 is less than or equal to M, it will be most beneficial if I have a big X because if I increase Y, it will be multiplied by a factor of 2, right? So, so what I am doing is I'm initially maximizing the value of X. X can be either minimum of CL or mid minus 1 by 2 because the initial condition X plus Y plus 1 equal to mid. So from here, the maximum value of X, the maximum X will come when X equal to Y. Okay. So basically, X plus Y plus 1 equal to mid. The maximum value of X will come when, as Y is greater than or equal to X, I'll replace Y with X and we'll get 2X plus 1 equal to it and X equal to mid minus 1 by 2. This is the maximum possible value of X and it will be bounded by CL. Okay. And the remaining part will go to Y. Y is simply mid minus 1 minus X. And what I'm checking is that if my currently assigned values of X and Y are less than or equal to M, then I'll set the value of L equal to mid. I'm basically binary searching on the values of the final answer. The final answer is at least 1 because our home base is always fortified and our final answer can be at most 10, the total n bases. Okay. So what I'm checking is if my correctly allocated values X and Y is less than or equal to M. M is the total number of days we have. Okay. I'll set the value of L equal to mid, else I'll set R equal to mid minus 1. And finally, my answer will lie in the variable L, and I am outputting that. And that's all. If I run the code, we can see that we are getting all the correct answers. In the contest, actually, I have handled, I thought that the one-sided cases should be handled differently. Like in the case where we go only one side, I thought that that case should be handled differently, and it led to some long code which I have commented out. And this code is simply the cleaned version of my contest submission, where I have removed all the useless comments. And that's all. Now let's move on to D question. D1, D2 are actually very good questions. So I'll start by reading the question. This is the easy version. You are given a rooted tree consisting of n vertices from 1 to n, where root has index 1. Okay. So we have a rooted tree with root 1, and each vertex is initially white. Okay. Let di be distance of root to ith vertex, and we can perform the following operations any number of times. We select a subset S of white vertices such that no two nodes in S are connected by a edge or have same distance to node 1, and color all those vertices in S as black. And our job is to find the minimum number of operations to color the full tree black. Now, if we focus on the first condition, what it says is that uh, in the set S, there should be no two vertices that lie at the same depth D. Okay. And also, like if we have two vertices x comma y in the set, depth of x should not be equal to depth of y for all xy, for all x and y. And also, uh, there should not be an edge between x and y. Okay. These two conditions should be satisfied for all vertices x comma y, for all vertices x comma y that belong in a set S. And in one operation, we can remove a set S of like a set S of vertices which satisfy these two conditions. Okay. Now our job is to find the minimum number of operations to required to color the full tree black. Like what we'll do is we'll remove, or in other words, we'll color all the vertices here black. Okay. And our and we have to find the uh, sorry yeah, we have to color all these vertices as black, and we have to find the minimum number of operations to color all vertices black. So here in this question, let's check the uh, let's make some observations initially. So from the first condition we know that dx is not equal to dy, right? So for finding the lower bound of our answer, we can say that if there are some five vertices at a depth d, all these five vertices should be removed in different operations. Okay, so our answer will be greater than or equal to maximum of uh, maximum of count of vertices at a depth d for all d equal to 1 to n. Okay. This is our first lower bond or something. And the second condition is that we can't remove, uh, we can't have edge between x and y, right? So let's take a case of a node having some five children. One, two, three, four, five children. Okay. If this node has five children, we can say that a nodes in a tree, all the children of a node are at the same depth. Okay. So all these five children are at same depth. So basically we have to remove these five in five operations or in five different operations. And here the catch is that in any of the five operations, we cannot remove their parent, because if we choose both a child and a parent, then the second condition will not be satisfied. So in this case, we need five operations to remove the children plus one extra operation to remove the parent. Total will be number of children plus one number of children plus one. We need these many operations. So our second bond for the answer will be max of 1 plus, not max here, we can keep the max inside. 1 plus max of uh, count of children for all nodes x, 1 to n. For all nodes x, I'll find the count of or number of children of that node x, and I'll add 1 to that value. And my answer must be greater than or equal to this. So seeing these two from our two lower bounds 1 and 2, we can say that our final answer is greater than or equal to max of count of vertices at a depth d for all depths, and 1 plus max of count of number of children. Here I'll right, count depth, and here the count of number of children of a vertex X. Okay, so our answer must be greater than or equal to these two values. And surprisingly, this lower bound is our correct answer. For proof of it, like actually the construction of D2 will be the proof for the D1. Like in this, we have to simply output the minimum number of operations, and they have given an ample amount of test cases. So in the contest, once I have checked this val answer is greater than or equal to max of these two, and so and when it came right for all 10, I have simply submitted it. But I actually proved it while solving the D2 question. In D1, in D1 they have only asked the minimum number of operations, whereas in D2 they have also asked we have to find a way to color the tree using that many operations. Okay, that's the difference between easy and hard version. So I'll discuss both of the questions at a time in this case. So coming to finding a way, it has a very beautiful construction. Here we can see now we have done, let's say that the value, let this value be k. So now my goal is to make the full tree black in k operations. So instead of visualizing this in k operations, we can transform this question as follows. Let's say that I have k colors, okay? And the condition is that uh, I should not have two colors at same depth. Like for example, I should not have two, like let it be zero. I should not have two ones at same depth. Like all the colors in a depth should be different, one, two, three, or let it be another parent, and all the colors will be different. And my second condition is that the color of every child should be different from the color of its parent. Okay, this is our two conditions, and we have to color the entire tree such a way that these two conditions are satisfied. Okay, so what I'll do is initially let's assume that k colors that we have are 0 to k minus 1, 0 to k minus 1 have k elements. Okay, so initially I'll color the root with 0. Now coming to the children of the root, what I'll do is as I have only one color occupied, I am free to use all other colors except 0. So I'll simply color it with 1, 2, 3, so 4, or and continue coloring. And if I have 5 children, I'll color it with 1, 2, 3, 4, 5, and so on. Next step will be these also second level nodes also have children, right? Now comes the tricky part. If we have only one parent, then it's fine. We can simply ignore one color and color with all others. But if we have multiple parents, like in this case, what we have a constraint that we cannot use one here and we cannot use two here and we cannot use three here, we cannot use four and five here respectively. Okay. And also all the colors in this depth should be different. I am traveling depth wise. Initially, let's assume that this is depth equal to 0. Now depth equal to 1, depth equal to 2. So here what I am doing is I'll just take the first child of every parent. I'll color the first child with red color. And what I'll do is I'll give Give the color of the previous parent to the first child. And obviously that will be cyclic. And the fifth parent color will go to the first one. Okay. So here this will get the color 1, this will have the color 2, this will have the color 3, this will have the color 4, and this will have the color 5. But main goal is to avoid the wastage. Like here, I cannot use 1, 2, 3, 4, 5 here. So I'm using all the parent colors such a way that they will be useful. And after satisfying this parent constraint, we are free to use all the remaining colors. Like for example, I have used 1, 2, 3, 4, 5 here. So leftover colors are 0 is leftover, 1, 2, 3, 4, 5 are used, and from 5 all other colors are left. Basically 0 and all other colors 6 to K. And I'll color them one by one. I'll assign this color 0. I cannot assign color 1 to 5. So I'll assign this 6. Hmm, I'll assign this 7, 8, 9, 10, 11. So here we can see that in the construction, first we are coloring the first child of every parent, and then what we are doing is we are coloring all the remaining elements. 0, 6. Here, why I am using 6 after 0? Because all the numbers 1 to 5 have been already used. So my next option is 6, 7, 8, 9, 10, 11. And let's say for even more clarity, if I have one more level, let's say this 0 has two children and this 7 has one child. What I'll do is, in the case where there are some nodes with no children, I'll simply ignore them. Okay? Ignore them in the sense, in the first step, what we are trying to do, let's go to the first child of 7 and give it value 0. First child of 9 and give it value 7. And taking the first child of 0 and give it value 9. Here, I am ignoring the values 6, 8, etc., which have no children. Because if they have no children, I am free to use those colors anywhere in the next depth, right? So here, after using 907, I'll again start iterating. Like I have used 0, then 1, 2. If I have more children, 3, 4, 5, 6, and I have used 7. So I'll skip that 7, and next I'll use 8, like that. Similarly, I'll follow this construction. So at every depth level, we can see that our first step is to assign color of previous parent to first child, and then uh, assign all unused colors. And initially, we have transformed the problem to coloring the tree, right? Here, basically, what I mean is, if I color the tree with 0, color with 0 means I'm basically selecting that node, uh, or I'll generalize the case. Color with X means I am selecting that node in Next operation. So my tree has all the colors from 0 to k minus 1. And if my node has a color X, I'm selecting that node in X operation. So basically, after coloring the entire tree, I'll simply iterate over all vertices and push them in a vector or something. Like all the vertices with color 0 are pushed in a vector 0, color 1 are pushed in vector 1, so on. And I'll print the vectors. So let's look at the output format. Initially, we have to output the number of operations k in the first line. Then we have to output k lines. Like each line should begin with an integer m representing the operation set, size of that set. And after that, it should follow with m numbers, like the basically the vertices, the m vertices which we are choosing in that set. And that's all. Okay. Now coming to D1's code, D1 is pretty simple. We have to write a simple DFS. Initially, I am creating a adjacency list, and we are taking the input and populating the adjacency list and running the DFS. So for every depth D, I am seeing how many elements are there at a depth D. Depth of n contains number of elements which are at depth I. Depth of I contains that, and child of I contains number of children of that current node I. So while iterating to adjacency list, I am incrementing the child number of children of current node Y. I am like traversing through adjacency list of Y, so I am incrementing the number of children, and I am pushing that in the queue. And after every passing every level, I am incrementing the value of depth. And our answer will be the max element of all depth and 1 plus maximum number of children of current node. So coming to the D2 code, initially this is just D1 code where I am calculating the answer. And if answer is 0, I am outputting that. This is outputting 0 and hitting the return. Basically, what happens in solve function is that if I hit a return, then it will come out of the solve and continue with the next iteration. So here it will come out of the code. Now what I'm doing is uh, here when they gave the input, I have populated as follows. G of I am pushing V in adjacency list of U and U in adjacency list of V. I am pushing both ways. So for just for clarity, mm, I am modifying the array G in this way. Like for example, uh, initially what is there is adjacency of list of 1 contains 2, 3, 4, and adjacency list of 2 contains 1, 3 contains 1, and also 4 contains 1. So what I want is I want to make it directed. So simply for everyone, for every element X, I am pushing only their children uh, in their adjacency list. Why I'm doing is that if we go to this implementation, it will be easier if I only traverse through all the children and I can get the first child easily. Like basically the first element in this adjacency list will be the first child. Okay. So after cleaning the tree, what I'm doing is I'm initializing vector into operations and n colors. N colors means not exact like color. This color vector contains the color of node I, and I'm initializing with n because I have n nodes. And initially, as I have discussed before, the root is color 0. Now let's start the BFS. What I'm doing here is that initially I'm checking the q dot size at every depth, and I'm pushing all the elements in the depth in an array. And I am taking the size of an array, size of that array. If the number of elements in the depth are 0, then there is nothing to do. And also note that here we are only pushing the elements which have a child. Like for example, in this one, in the second case, what we are doing here I am taking only elements which have children, right? I am ignoring the element 1, 2, 3, 4 as they have no children. And I am applying the same operation. Like they select only the vertices which have at least one children and assign the previous parent to the vertices. Okay. So we can simply ignore the ones which have no children. So if g of y is not empty, means at least it has one child, then only I'm pushing in the array. And if the array size is 0, I have nothing to do. Everything is color. And if the size of the array is 1, what I'll do is size of the array 1 is the first case. First case is or at depth 0, what we are doing is except 0, I am using all the colors, right? So generally, let it be not only 0, let it be some 5 or something. If the parent color is 5 and it has only one parent at that depth, what I'll do is 0, 1, 2, 3, 4, and after 4, I'll color with 6. I'll just ignore this 5 value. So I am putting initially the danger color is the color of the parent, and I'm visiting all its children. And if the current value is not initial current color, let the initial color be 0. And if the value of color is danger, then I'll increment the current pointer. Current pointer is basically a color which I keep on incrementing it. And I will color its child with the current color. And I'll again increment the current pointer because I have used the value current. I'll go to its next color and I'll push it in the queue. Else, here we have handled the case where there is only one element at the current depth, and if there are more than one element, now we have reached the case where where I have to color with the previous parent. This one, we are coloring the first child with the color of the previous parent. Okay. If g of y dot empty continue, this is just a safety check, and we are coloring the first child with previous parent color. In the array, for ith element, I minus 1 is its previous element, and just handling the case of 0, I minus 1 plus size, modulo size. And this is the first child of the current element. What I am doing here is I am assigning the color of the previous parent to the current element X. And I am maintaining a set used to track all the used colors, and I am inserting the used color in that set. Okay. All the remaining colors other than the colors that are in the set use are safe. So what I'll do is I'll simply iterate through this, and as I have marked this value as visited, so I can safely iterate all the value. Only the first child will be visited, all others will be unvisited here. So in this second loop, all the children other than the first child are being colored, and while the current color is not in the use set, I'll increment this pointer and I'll color it with J. Basically, J is the initial color. I'm taking the color as 0. Like for example, what's exactly happening here is if my current color is 0 and my use set is 0, 1, 2, 5, 8. So what will happen is initially J equal to 0, right? While the value of J is not in this set. Like while use dot contains j, sorry, while the value of j is in this set, I'll increment the value of j. So initially the value of j is equal to 0 is in the set, so I'll increment it. J is equal to 1 is also in the set, I'll increment it. J is equal to 2 is in the set, increment. Now we'll get j equal to 3. which is not in the set. So what will happen is it will come out of the while loop. Then I'll color it, color the value of no, color the node x with j, and I'll increment the j value, and that's all. And finally, what I'm doing is I'm iterating through all the vertices from 1 to n and pushing them. Basically, color I means the vertex has been used in ith operation, and I'm pushing that in the operations vector. And initially printing the answer. And after that, we have to initially print the size of the number of elements in the set in ith operation, and then we have to print the value of all the nodes in ith operation. And that's all. I guess we are done with today's contest. Thank you.